Good afternoon, everyone. I'm Giorgio Mogli and I'm a PhD student in electronic engineering. Today I'm going to present something of my PhD project about 3D printed tactile sensors from natural sources. But first of all, a brief introduction of myself. I achieved both the bachelor and the master degree in biomedical engineering, and during the master thesis, I got in touch with the fabrication of hydrogel-based wearables. This experience led me to start a PhD in electronic engineering focusing on 3D printed tactile sensors. And during this period, I worked at DISAT, and I had also the opportunity to study natural polymers for sensors at Scion Group in New Zealand. Now let's move to the research complex. With the technological advances, the humans and machines interact more and more frequently nowadays. But these two realms are so different. Humans are soft tissues, while machines rely on stiff materials. Therefore, there is a critical need to build a bridge between these two worlds. And tactile sensors, namely soft devices that can convert physical stimuli into electrical signals, could fill this gap, finding application in several fields, ranging from prosthetic to soft robotics, wearables, and so on. Current challenges in tactile sensors include finding materials that are both flexible and conductive. Flexible polymers have often lower sensitivity and face scalability issues compared to rigid sensors. Additionally, balancing properties like flexibility, durability, and conformability is really challenging. Finally, the growing problem of the e-waste highlights the need for sustainable materials and power sources in electronics. Therefore, the core of my PhD project was developing green, flexible, piezoresistive sensors using 3D printing. And I focused on hydrogels, namely soft polymeric materials that can retain a huge amount of water, that can be made electrically conductive through salt dissolution, resulting in stretchable and conductive materials, as the one that is made by synthetic polymers displayed in this picture. Given their conductivity, these hydrogels can be used as a piezoresistive sensors to detect applied stresses or strains. But more interestingly is that the developed hydrogel can be 3D printed, enabling the fabrication of complex objects with a good resolution and optimal conformability to regular surfaces, like the mesh that I have in my finger. By testing these objects as force sensors, we observed that resistance variations strongly depend on the sensor's shapes. In particular, softer geometries exhibited greater resistance changes under applied stress, since they deform more under a same given force. This highlights that sensitivity to external forces and deformations can be tuned through object structuring. However, currently soft sensors mainly rely on synthetic polymers. For a more sustainable approach, it is important to move towards abundant natural materials. Using cellulose and gelatin, we developed an all-natural formulation by which different compression sensors were 3D printed. In this case, the sensitivity, once again, was enhanced of 2 orders of magnitude through different 3D geometries. Moreover, the hydrogenous liquid phase, a glycerol and choline chloride mixture called eupectic solvents, enables long-term stability of sensors by preventing water evaporation. In addition, when placed in the soil, this material degrades in few weeks, as the naturally present microorganisms in the ground break down the polymeric networks without releasing harmful components in the environment. Plus, due to their optimal ionic conductivity and flexibility, these gels can be used as electrolytes for flexible supercapacitors. By integrating the supercapacitors into the printed gels, self-powered sensor system can be achieved. Supercapacitor can be charged with green sources like flexible solar cells and then act as power supply for the sensing components. Finally, let's see some potential application of these 3D printed sensors. They can be used as wearable to detect large deformation or small deformations, or they can be used also to build customized human-machine interfaces like the joypad reported on the left. To conclude, 3D printing represents an effective way to enhance sensing properties of soft sensors by tuning object shapes. In addition, fully natural polymeric networks with good printability, conductivity, and stability over time can be developed in order to build more sustainable devices, not only for sensing but also for energy storage.